Okay, so let's get started. So today we will talk about, again, reinforced learning with from human feedback. Last time we talked about the reward modeling, and now we talk about policy learning. Of course, the goal of reward model is really for the purpose of policy learning. So today really is a key part in basically how do you train your large language model so that it can behave better, align with human preference. So we will mostly talk about two algorithms today. One is which is pretty popular algorithm, DPO, direct policy optimization. Another one is also used, both algorithms are used quite often. I mean, both in the industry, also in research. The other one is rejection sampling, or it's raft. So we will talk about these two, and for the policy learning. Then we will talk about how this general RL works versus what is RL versus supervised learning. So this is essentially the topics. Okay, so here is outline. So again, we will just review the background, which we already have last time, basically on the alignments, reinforced learning from human feedback, and so on the background. Then we will talk about the derivation of these, the first algorithm, and just continue from last time. This leads to the so-called DPO, direct policy optimization, direct preference optimization. Yeah. The iterative DPO is something more aligned with the typical RL workflow. At that time, we will try to explain why we need that and so on. So this is just a refinement of the DPO in terms of RL. DPO is more like a supervised learning, as we will see why the iterative DPO is more like reinforced learning. Then we talk about raft, which also has reinforced learning. For the first method, DPO, turns out we do not need a reward model, as we will see later. So we mentioned our typical RHF workflow is you have a reward model, then you have policy learning, right? So one of these approaches doesn't need. But for the other two, the iterative DPO versus or the raft, both will require reward modeling. So that's more aligned with RL. Okay, so let's look at that. So let's look at the RLHF. Recall that this one is reinforcement learning from human feedback. And the data format, as explained to the in the last time, will be preference data based on human feedback. So essentially, you have a prompt, you have two responses. One is preferred over the other. So this is generally the data format when you train this RLHF. For the reinforced learning, the typical workflow is like this. The first, you learn a reward model. So this is based on the preference data. Essentially, R is a prompt, and A is answer. So basically, this one we covered the last time. Then you learn this is a Bradley-Terry model, and then you have used logistic regression to solve that model. The second part is policy learning. Policy learning is where we want to focus on in this lecture. They basically try to use this reward model to optimize your LLM, which is so-called policy, which is pi of essentially, it's a conditional probability distribution. It's pi is a probability distribution of A is your response, given X, which will be your prompt. So basically, yeah, this is a notation. which is given. And recall that last time we mostly talk about reward modeling, right? So and this time we will talk about policy. So basically, this is what we plan to do. For the first algorithm, actually turns out the DPO, direct preference optimization, it does not require reward model. As we will see, it's a related, but once you derive that, it bypasses this reward modeling. So this is the first algorithm. And then we eventually argue why we still need a reward model and so on. So one popularity about the first algorithm DPO is it bypass reward model, so you save one step, right? But then you still has some other effects which requires you actually doing something else. We'll talk about that later on. So yeah, so this is policy learning. So if you recall last time, right? So we talk about the reward model. This one will come back soon when we talk about the direct preference optimization. So this is a reward model, but assume this is learned from preference data. If you recall last time, this is learned from BT model. So this is you can learn from the data. When you do RL, which is policy learning, try to learn your pi, which is policy. You do not have to do the same data which learns the reward. If you recall the last time, right? When we talk about instructor GPT, that model they have different data to learn reward and a different set of prompts to learn the policy, right? If you recall, the reward has a more diverse set of prompts, and the policy has a smaller set of prompts which are more targeted for the customer prompts. So essentially, it's based on what OpenAI gets from the customer, and then you train that. A common policy optimization is this objective function. So the objective function is you optimize the average reward here, right? In the same time, you also penalize basically you try to encourage your policy to be close to the PyRef. PyRef is the policy which you start before the RLHF policy training. So this one is just to refresh. This is from the last time, and the reason for that, if you recall, is that you do not want policy to drift far away from the reference. If you drift far away, there are issues about losing diversity, right? They will forget some knowledge you learned from the pre-training or instruction tuning. And also there's an issue about reward hacking and so on. So in the end, this regularizer try to make sure your policy learned is close to PyRef. There's tuning parameter there. Basically, this is how it works. So beta is a regularization parameter, and the PyRef is a reference model. So yeah, okay. So this is just recall. Now this lecture we want to say how do you solve that, right? So how do you solve the policy according to this model? One thing about this, which we will come back again in the later on when we summarize RL versus supervised learning, is that this one is say you take a set of prompts. This expectation actually says you are generating the response from your current model. So basically your data, this expectation really is data. This one is the reward, is what you want to optimize, but this is a like loss function, this one reward. This one is the data. The data itself actually says that your data should be generated using your LLM, current LLM or current policy. And this is the key difference of reinforced learning versus supervised learning. Right. Supervised learning, they always given data, static data, which does not change when you change your policy, right? You always have a gold data, you can call that, which are reference data. For reinforced learning, the data generated by your policy. So you are directly optimizing your policy, both in terms of your data and in terms of your optimization, policy optimization. And of course, when you generate the data, you want to say which data is good, which data is bad. And the objective function here, the loss is really says when I generate data according to my LLM, right? How good it is. So it's reflected by this. Again, it's you have a higher reward, it's better. This one says 1 pi close to pi ref. The KL divergence small is better. So yeah. So generation quality, as always, you have to understand in this context, there's a trade-off of generation quality versus generation diversity. Usually is measured by closeness to the reference model. Certainly, when you make it close to the reference model, a key part which we write here is diversity, but there are other effects, right? If you recall, we mentioned other effects is one is reward hacking. It's basically your policy is very similar to your reference, so you do not see a lot of reward hacking. The other one is your pre-trained knowledge gets preserved. So, but diversity is usually people measures when they try to look at RL. Here is something which is pretty important for this lecture, especially for the derivation of DPO. The DPO is basically based on this formula. So this formula is well known and also used in the raft paper, but this one is critical for the DPO paper. So we will give a proof of this. Essentially, to say, okay, optimization of one, which is basically reward minus KL, right? Will be given by this guy. So this guy, what does it say? This guy is pi is a kind of proportional to your pi ref, but it's weighted by your reward. Divided by this beta, right? So beta basically means it's exponentially. It's have a exponentially, essentially a larger reward. You should have a larger probability. If you read this, right? This is original pi ref, which may give some good answers, smaller probability because it doesn't have a risk reward. But after you are solving that equation, what you really get is some reward, is your pi ref, and weighted by exponential of a reward. Of course, the larger this one is, the larger reward is, the larger of this is. So the larger of overall of these two terms is, and this term is a so-called regularization term, which appear quite a bit both in the softmax logist regression and later on when we do the energy-based model. They all have this particular the normalization is summing over OA, so that this is a probability. Basically, this is say sum of this guy to be 1, which means pi star A conditioned on X is a probability distribution. This is quite common. You see that quite a bit of other things, but essentially this is the key to say when you solve this kind of RRHF, especially entropy regularized, what you are targeting, what your fine-tuned or reinforcement learned distribution is like, and it's basically like this. It's basically like pi ref times weighted by some exponential term of your reward. Okay, we'll prove that. But before that, is any questions about this particular form? This form is pretty important in the RLHF literature. Yeah, it's reasonable to understand. Okay, so let's try to give a proof. Proof is a little bit short, but it doesn't necessarily require. You can always recall that we do not need to have the proof, right, to have the exam. But here is what it is. This is the original objective function. It's a given any pi, right? So I have a q pi, which is our objective function. The larger, the better. If you recall the previous, you want to maximize this objective function. And it's written this way, right? So you can, here is what it reads. It's just move this r to here, right? So if you make a r to here, it just, this is a log. Log, you compensate by exponential. Because these are beta here, you compensate by divided by beta. And because there's minus, and this one is divided, is when you compensate the log is minus, therefore it becomes a log of this one times this, okay? So this one is, this one I hope is, it's just algebra. You just move this r to here, and then you need to take exponential, right? You need to compensate by beta, and you need to compensate by the negative sign. So basically, it's become this. Okay, this is very easy to check. It's a high school algebra. Once you have this, then if you look at that, I just have this definition, right? This is just a definition of pi star. So I will replace this guy, it's basically here, by zx times pi star, right? So basically, this is here, right? Essentially, it's a replace this guy by zx times pi star, just by copying this guy, okay? This definition, this one just a definition. Now, if you have this, what you can have is, this is a KL term. So this one is a KL term. This z, you can move it out of the log because it doesn't depend on a. Oh, sorry, this one should be expectation of x, zx. So I think I need to write expectation of x, zx here, okay? Just missing expectation. But because some of it doesn't depend on a, this expectation doesn't take. So basically, it is a beta times expectation of x, zx minus that. But nevertheless, this one is a constant. So here is missing of expectation. I will add that up. But essentially, it's a constant minus KL of pi over pi star, right? So this is basically the formula you will see from Q pi. This is always the case. A constant minus this guy. Then what is the largest number of these? Because this one is always non-negative. It's a KL term. And the pi is equals pi star will be the optimal solution, make this 0. So if you try to work it out, you pi q star minus pi q pi, right, is basically pi q pi star will be beta times expectation of zx here. And this guy is this. So basically, you subtract these two, you get this guy. This guy is always larger than 0, which means pi star is the optimal solution of that. So this is just derivation using algebra. The algebra is mostly to do with the definition of KL and the high school algebra. And then you recognizing that the KL of two distributions is always non-negative. This is a standard result for information theory, right? So basically, yeah, basically this is this one is essentially what we need. So basically, the main point is the following, right? So you can read this later on. I just go through this. It's not too difficult, except that there is a missing expectation x here. Essentially, this one is you recognize that pi star will be normalized distribution such that is a reference weighted by r. The larger r, you are boosting your probability of this response. Any response A with a large r will get boosted, right? And if respond with a lower r, it get be demoted. So this is a formula. We will take this formula. Just remember this one is this formula. And we will rewrite in the next slide, and then we will derive the DPO. DPO is essential. What if you see that what happens is the following? So you have a reward model, right? You have pi star. So these are related, optimal pi star. So you can write a reward model in terms of pi star. So in this case, if you look at it, this is what we're next to do. And once you can write a reward model in terms of pi star, then you can realize that if this one is your LLM, has some trainable parameter, you get a trainable reward in terms of your policy. And therefore, you can direct optimize the policy, basically. Here is what it is. You rearrange that. Reward, it's basically based on the previous slides. Reward is always this formula, plus beta times log zx. This one is a summation term, which we do not care too much about because the reward we care about it's a preference, right? Preference means you want to say whether A1 is larger than AB or not, A2 or not. If this guy doesn't depend on A, you can ignore that. You don't have to take care of that. The implicit reward given a policy is this form. So this one is, say, any policy you're given, assuming it's an optimal policy, then you can imply a reward by this formula. So this is a key for the derivation of DPO. Okay, so let's go ahead. The term does not affect preference ranking because it doesn't depend on A, right? So, and more explicitly, if I have a pair A1, A2 under problem X, and this one cancels if you just you derive minus this one, right? So basically, you want to say which one is larger? Reward of A2 is larger or reward of A1 is larger. So only depend on the implicit reward minus, not depend on this guy minus, right? So basically, because this cancels, so this one doesn't depend on A. It's a summation term. So this guy is just say, okay, this is real reward. If you solve your optimal policy, it will be the implicit reward minus. So this is the optimal policy. This one is reward, and so on. Okay. Any questions so far? Last slide. Previous one.
What is the Q pi star? Yeah.
Oh, Q pi star is pi star is this guy. Q is objective function. It's here. It's actually it's given. Yeah, I think you come late. Maybe I will come back to this. It's defined here. Yeah, this is what you want, and pi star should be. Yeah, this one maybe writing pi star. Yeah, yeah. But basically, Q is this objective function, and you want to say a pi star maximize Q. Okay. Yeah. So. And this one gives you the proof to say pi star is the largest possible value, because for any Q pi, this is non-negative. Okay, so yeah, so this is something if you are interested in working in this direction or whatever, RHF and so on, this is some formula you should really need to know or remember. And this one is the derivation key term in derivation DPO, which is basically says reward can be written as a policy. Okay, reward can be declared using policy. Now let's look at that, right? We recall the BT model, which is from the last lecture, which actually can train a reward model. For any reward, it's given by this guy, right? And because we have an implicit reward, is all reward can be parameterized by policy. This can be a learnable policy. And this one is a reward. Then your reward model, you can say, oh, if my policy, my LLM, real LLM is like this, then can use by replace this reward by my implicit reward of your policy. So this is the implicit reward from your LLM policy. This is a real reward. And because we have a relationship, when we solve this LLM, so we have to do that. Okay. So the idea is we want to use this implicit reward. If pi is trainable, then the implicit reward is also trainable. Then we will train this directly. So BT model will become from this guy, original from last lecture, to this one. This one you can think about the parameterization form of R, because R is replaced by implicit reward. I mean, is that clear? Or any questions? Yeah, go a little bit slower because I just want to make sure this is a little bit mathematical, but make sure people understand at least the main concept. Yeah. how it works. So last time we talked about the logistic regression with reward model. We didn't say what reward model it is, right? Actually, in the instruction GPT, if you recall, also in our homework, you will recall that there will be one which you just using LLM. You remove the next token prediction head by reward model head, and then you give you the reward. So that is typically what a reward model look like. And it's a smaller model. If you recall last time, it's an 8 billion model versus a policy model of 175B. Okay, this one will come back. I just want to remind you the last lecture. So for our reward model versus policy. But here you just say, okay, let's just make this reward to be a policy, right? If you think about the instruct GPT, right? That paper we talked about last time. Then you say this policy certainly is GPT-3, right? It's a 175 billion model. And then essentially you can say, oh, I can use this model just to solve. So that's basically the idea. Direct policy optimization. Basically, they say it's a BT model. We have a maximum likelihood estimate, which given preference data, because we know we have a preference data to train reward model. This one is the implicit reward. And this is, let's say, trainable policy, which is your LLM, right? LLM, you can train your LLM parameters. It's a transformer, right? So you just train this transformer, and then this one gets you whatever you want. So this is just a different loss function. This formula is called a DPO. Actually, I think I made it incorrect. I just realized it's not a direct policy optimization, it's a direct preference optimization. I also need to change this. Direct preference optimization, but the DPO, it utilizes the relationship of optimal policy and its implicit reward to optimize policy directly from the preference data. Essentially, you'll say, okay, I have a policy, just repeat this, maybe just a little bit. I have a policy that have an implicit reward given by this optimal solution of your policy reward relation, which we proved. And then using that implicit reward, I can use directly treating a policy as a reward model. Right. So and the reward model then just just using this this one is the same. So essentially, compared with the normal reward model, let's just look at the instruct GPT as an example again. Right. Typical reward model, you have 8 billion reward, and it's will be a policy with a detached hatch. The head will be changed from your policy to be a classification head. And then here you just say I will just using which is 8 billion, right? Here you just say I will want to use 175 billion GPT-3, right? To do this. By doing that, I'll just directly optimize GPT-3 on this particular data, preference data, with this, right? So we will talk about that. I mean, keeping this in mind so that when we talk about the iterative DPO, then we will understand a little bit better. So why the motivation there? But here, then basically this is the DPO. So this is the DPO. Here are the experiments about the DPO. So the experiments are the following. So the left, this is coming from this paper. Basically, it have a subtitle. Your language model is a secret reward model, right? Basically, this is basically talk about the implicit reward, which we talked about previously, which is based on the optimal solution of your KL regularization formula. So because it's an increased reward model, you implicit reward from the DPO, then therefore you can directly optimize your policy through the optimizing of this implicit reward. So this is the derivation is before. So here is basically, just say they do some good results and so on. So I don't want to go over detail. PPO, I want to say this. PPO actually works pretty well, but it's a very difficult to tune. So one advantage of a DPO is especially in the open source community, right? You tune that much easier. So this one is just a logistic regression, right? So you just plug in your language model. You don't even need to do reward model. Just run the logistic regression, and then you are done. We have this exercise. Actually, it's also given in as a notebook, but you also probably can re-implement in the homework. Essentially, it's much easier. BPO is tricky. We are in this class, even for the next lecture, we will only talk at high level about what a PPO is. We will, if it goes to implementation, it's quite tricky. I mean, I would say even next lecture, there are something called a GRPO is also make it simplified GPO. So PPO is not easy to implement. And so only in the frontier labs, they can have a very good implementation. Open source, the implementation usually not up to there because there are a lot of tricks, whatever, to get it to work. So DPO, compared with that, everybody can implement very easily. PPO cannot. Yeah, there are a lot of tricks. Yeah. So they say our implementation. So clearly from their implementation doesn't really mean they are good implementation, right? So just want to comment on that. Yeah. But nevertheless, good implementation is not easy. Yeah, even for something like TRL, whatever, the people always complain. Yeah, it's tricky. The left is this guy. The right is on another side. So that's how they talk about different things. Let's move on. Summary: DPO bypass implicit reward model training by using the closed form relationship between KL optimal policy and implicit reward. And this is a key. You do not need a reward model. So that makes things a lot easier, quicker to implement. Practical consequences is much simpler pipeline, right? So it's a supervised learning pipeline. It's not a reinforced learning pipeline. So it turns a reinforced learning problem by using this implicit reward into a supervised learning. Recall that when we talk about reinforced learning, also later we will say it again. Is in reinforced learning, your training data should be generated by your policy. At least partially, the trajectory. Supervised data is just given by whatever others. Supervised logistical objective easy to tune. Compared with PPO is much, and also it's a reference model constraint because it's coming from the KL regularized formulation, so it's a constraint. So also this is a nice behavior. You can tune your beta. The larger the beta, the closer your pi star to pi is. Yeah. Do we need a reward model? So if I recall, this is the tool, right? So usually we have this guy. Again, I want to make a comment. Of course, if you say when I ask this, probably the answer is yes. But one justification, if you remember from the last lecture, right? Here this is reward model. This is policy learning, either PPO or some other method. Other method we will introduce. One is like a raft. Will be another one. But the reward model is part. Recall that in the InstructGPT paper, right? So 8 billion. So this is reward. This is 175 billion. Okay. Here you just say, forget about this 8 billion model. You directly over the LM, right? Over the policy of 175 billion model. And you are bypassing this reward model. And usually another thing is reward model and the policy model, usually they have different distributions in this case. You could allow that in this. In this case, the distribution training, this is going through the reward model, right? Parameterization of this particular, because it's an implicit reward, is equivalent to a reward model of 175 billion here, if you do the PPO, if you do the DPO, right? Reward model, 8 billion, here is 175. Then you say, oh, you have much larger. If you recall last time we mentioned they run into issues when you have a very large reward model. And the question is, is that desirable? Right, two approaches. You have smaller reward model typically than train on policy. The data may not be the same. Here, you bypass reward direct training, right? Induce an implicit reward. So this is do we need reward modeling? And the answer is yes. And if you have a simple sentence to say why, is it is easier to train a high order reward than high quality policy. I mean, reward is a judgment. Judgment is easier than generation. So that's That's typically the case. Recall, again, I just want to, this is 6 billion. Yeah, I forgot it's 6 or 8 billion. I think yeah, okay, I will check back because I always remember it's 8 billion, but maybe it's a 6 billion, not 8 billion model. But nevertheless, it's a much smaller model than this one, right? Because this is an easier task. Also, you have benefits of. So when you say, okay, I can bypass this easier task, I will just make it a hard, difficult task, then there must be something is missing, right? So the main thing is, this is in this study made it clear, but there are other studies of similar results, says implicit reward from DPO is inferior to at least on out of distribution data. So basically there's a practical consequence. And because of that, if you really want to say, I want to tolerate a little bit more out of distribution, it's better just using a reward model instead of implicit reward from large model. So DPO policy is inferior on out of distribution data. This is this paper did some study on this. And we'll talk quickly about these studies. So then we will understand what it means. Okay, so here is the kind of study it's done by this paper. Basically, it says you have two kind of distribution, right? One is prompt shifts. So for example, your prompt is not your training data, right? Your prompt may be evolving than what will happen, right? So the other one is a response shift, right? Basically, it says, so even I have prompt the same because I'm continue optimizing policy, right? The policy response will be different than the prompt with your preference data, if you recall. And this one is actually pretty crucial if you recall that because you are optimizing your policy. Your original prompts response is given by maybe your old policy or your some human-generated policy, which may not necessarily be the same as your LLM generated policy, the generated response. LLM generated response can be different. So right. So basically, yeah, there are some examples, yeah, essentially. Basically, yeah, it's just different changes. Okay, then once you have this outer distribution change, which is pretty common, especially this one is pretty standard. This one also important when your customer or something new things come in, right? You have new terminologies or new different news, then this can shift as well. So basically, yeah, both matters. And the results roughly says, right? If you look at the explicit reward versus implicit reward, right? So so after distribution data here, this one is in distribution. In distribution doesn't make too much difference, right? But after distribution, you see that it actually get more of a difference, especially some of the data could. But generally, explicit reward means you're using smaller model, right, to model your reward function. Implicit reward, you just directly using your policy model to train your reward, and this one turns out to be more robust. So so basically it just says that. So yeah, we don't need to go to too much detail, but the conclusion from this experiment just say when you have a distribution shifts, you see a more of a difference. Yeah, okay, this is ID means in distribution. OOD means out of distribution. In distribution, they are similar. Out of distribution, you see a more larger difference. Okay, let's talk about then what is the solution, right? If you're using DPO, you could still get an explicit reward model as a judge with the current policy to generate the preference data. This is more aligned with RL frameworks. We will come back to that soon. Basically, just iterative a few times. You just keep generating, keep using reward model to give you judgments, right? You need a generation is by using the current policy, for example. and the judgment is given by your reward model. And then you solve this problem. Then you can use DPO to iteratively optimize your policy. Iterate. First, update policy using current reward model. This is through the DPO, right? DPO, you have preference data, you can get your this guy. And then you update the policy to generate responses for each prompt. And then you basically you use this update policy to generate responses, and then use a reward model. Now here is an explicit reward model comes in, which you can generate the preference data. Now you just iterate. So this idea is pretty straightforward, but this one is more RL pipeline. The reason is this kind of iteration is RL instead of just supervised learning. The reason is here, right? Here, this one certainly just say it's kind of an AI feedback, right? You can say this is an AI feedback, it's your reward, but here is your response is generated by your current policy. Once you have this step, it becomes reinforced learning because your data coming to the next DPO iteration is generated by your policy, not by the prefixed data. It's not supervised data. Is that clear? I mean, the conceptually? RL versus supervised learning. Okay, yeah. So once you have that, you have RL, right? So then you are done. So this one is policies learned from explicit reward model, and then it's more out of distribution data. This is a claim. We will have quickly. There are a bunch of papers talk about that. There are more papers, but I will just mention some of these papers. And here is kind of the quick results from the, basically, this result says following, this base model is the same, right? It's just a reference model they start with. Then after one iteration, it improve pretty well. This one is called win rate over GPT-4. It's a small model trained, but then win rate means whether you can have a judge, right, to say whether prefer your response versus GPT-4's response, right? They just, and we have this kind of win rate calculation in the homework, just using very, very small examples. You can check that. Essentially, you have this is like a AI judgment, like aligned with the AI, what they call the RLAIF, right? AI feedback. So this is this could be a human judgment or AI, but essentially, iteration 0, you improve quite a bit. Win rate, this is a very small model, so that's why win rate is small. It's like 10%, 13%, right? Iteration 1, it actually generates faster. If you use explicit reward, you go more quickly. It turns out what's interesting is that even using the DPO's implicit reward to rewrite data, you can still have some improvement, but quickly it's saturated. It doesn't improve a little bit, but you do see a little bit of improvement. But especially for the explicit reward, you see quite a bit some improvement. So basically, yeah, this conclusion says you do want to do this iteratively instead of treating that as supervised learning problem. You treat that as a reinforced learning problem by iterating over the data. And the key, of course, is that your reward model judgment is simpler than generation. So that's why this kind of process works. This one is coming from this, yeah, and the last, yeah, this mentioned the last control is for reason because usually they prefer longer. So human also prefer longer response. They seem to be more serious, but so that's why you need to control the length. And the base model is a small model, very small model. Yeah, it's a 2B model. GPT-4 is certainly a very big model, right? So basically, yeah. So that's why its win rate is small. It's like a small. But anyway, so that's about it. So let's just because no, from a DPO, right? That's considered a supervised preference directed learning to RL, right? I mentioned the generating data, so I was just coming back to the RL terminology, which then you can have better understanding. In the RL, then we will talk about the other methods, right? So next. In the RL terminology, we optimize a policy based on reward model. So this is essentially, reward model is learned by supervised learning. So there is no RL in the reward model learning. It's just supervised learning. But here we will talk about RL. RL means what? Means is the following. Reward is basically evaluate response quality, right? So this one we know. Policy is maps prompt text to response action, A. Yeah, okay. A in RL is always a call to action, but in our case, maybe we count answer or response. A becomes. But essentially, this is your LLM. Okay. But RL usually means action. Yeah. So this going by our terminology. Then there's two things, right? Trajectory generation. This is the key part which is different from supervised learning, as I mentioned. Is how do you generate by the policy model, right? Your policy model, you use that to generate the data. X usually is fixed. The prompt is not generated by the policy. It's just given. So that part is given. But the A is your response from your LLM. They are generated by your LLM. It's not generated by human or other things, right? So you generated this one. So this is something which is, as I mentioned, this key difference. Key is RL, and the trajectory is generated by this. And certainly, it's also rated by reward model, right? That one we know. How do you say, okay, generate trajectory? Then what you do, you give a rating. Each trajectory a rating. Rating is given by reward model, okay? And the policy update, improve this policy using trajectories labeled by reward model, right? So, and essentially you have a trajectory. This is called, when we say trajectory, is basically data generated by your policy. So that means trajectory. Again, these are our terminology, and then essentially you want to update. So this is, compared with the supervised learning, the key again is that use a fixed data set in supervised learning, right? We never change their data set, X, Y, and they're fixed. RL repeater generate new data from the current policy. So that's the key differentiation. Yeah. Actually, it's conceptually. Any questions so far? Okay. So yeah. So now if you're using this terminology, you can say question is, right, is a DPO RL or is a DPO iterative DPO RL, right? So DPO, you can say it's more like supervised learning, but it works with the preference data instead of the Euro data. Euro data means classification type of data, regression data, right? That is typically when we train a reward model, but or when we train classifier. But the preference data is using the BT model, and then you have preference DPO is more like a supervised learning, bypass the reward using the implicit reward to optimize policy. It never changes changes the data, so it's kind of supervised learning. While iterative DPO, it does use generation and rated by reward, so it's a RL. Okay. Either DPO policy, right? So you start with a policy, then you have a new response, right? You new labeled data. This is rated by reward. So this label comes from the reward model, right? And the new policy, right? So this is a loop. RL is a kind of a loop. You iteratively improve that. That's the general, yeah. And well, I mean, if you understand this, and roughly you understand the RL, at least it's much easier, I think, for this lecture, for the next lecture, basically. Yeah. So this is the simple version of RL. You keep doing this loop. And there's a pipeline. Later we'll talk a little bit about our policy next time. But essentially, for the on policy training, usually this is general framework. What I'm saying is, you iterate. This is on policy training, right? You first generate trajectory using the current policy. Rate the trajectory using reward model. Again, this is more to do with RLHF. Other RL is similar, but you know, there are some variations about something. But and the filter or weight. When we say filter, we will talk about next for the raft, and then you can compare with the iterative DPO. Then you see the difference. Update the current policy, and then you just iterate. Right? You always generate new data using the new policy. And then you use a reward model to rate this data, how the quality of this data, and then you generate it, and then you iterate. So that's RL. So typical RL iteration. and this guy is like this. Okay, so here is on policy, and the current policy, right? Start to generate the trajectory, rate by reward, and update policy. Then you go back. You go back. The update policy becomes the current policy, right? So and then you just going over and again. So this is a standard RL pipeline. So policy not only for the learning. One thing is here is making it a little bit more complex. Also from infrastructure point of view, they also require something different. Is a policy you also need to generate the data, both generate the data and the learning. This part is the learning update your policy is where the learning comes from, right? This one is you are generating data come from. So basically you have to do both. And then you have to say what is the infrastructure wise they need some additional things to handle this kind of pipeline. That's supervisor. Supervisor learning data is static. You don't need the data. You don't need to generate the data. So here you need both. Okay, so now we'll talk about another one. Another one is actually also using the same. You can understand pretty simply if you understand this pipeline. Recall the DPO or iterative DPO. You are using the preference data, right? But we also know, if you recall the instruction tuning, we also know we can train a policy, update the policy instead of using preference data, using just the non-preference data, basically prompt response, supervised data, right? SFT data. SFT is a non-preference data, right? When we talk about SFT. And of clear, just rough data is compared with DPO. You say I use FFT data using the RL lookup. And how do you form this SFT data will be what we will talk about here. Same look at standard RL framework. Your policy generate the data. Reward essentially, okay, here is actually what it is. You reward, so how do you generate the FFT data? For your generate data, some will be high quality based on reward, right? Some are lower quality based on reward. Then instead of forming a pair, comparison pair, which is preference data, you just forming a filter out some quality data. So if let's say I have a pair, larger reward, smaller reward, then we just remove the smaller reward, right? Or just keep the larger reward. And this one actually also works if you think about that, because each time you get higher quality data according to your reward, and then you update the policy. So basically, this is an idea about this algorithm. It's actually a little bit simpler if you think about that. You do not work with preference data. You always work with SFT data. I hope that's clear. Once your reward model. Again, this one assume you have a reward model, right? Policy generates sample k and some temperature, and then you do top k. You look at the yeah, maybe it should be one of that. Basically, yeah, I have a two slide. Actually, maybe it should be one, but essentially you picked top. Yeah. Actually, you generate the k samples. I think there's something top one of these k samples. I will change a little bit. Yeah. Top one of these k samples, and then your SFT update. This one is your reward pair, right? If you choose two, it could be two, but let's say just choose one. Yeah, I will change this a little bit. Yeah, top one should be top one. Yeah, just and then you update. Okay. Top k filtering is based on the yeah. Let's say filtering is based on entropy regularized reward. Right. You can use this guy to regularize your reward, and then you just compute for each trajectory. The larger, the better, and then you just pick the largest one. So this is basically what it actually how it works. So I'll give algorithm, but from this it's hopefully it's a rhythm clear. So this is a rank. You have a ranked list, and you pick the top one, right? Top one, and then you keep that. You go through next SFT. Basically, you form SFT data with X this guy, and then you come, and you just remove this lower quality data based on your reward. This is RL loop, because each time you are using better data according to a reward model, And then after that, you are generating using your policy, and you are iterating. Okay. This is used quite often. It's also, in some sense, it's simpler than DPO. If you think about DPO at this step, you are working with the preference model, right? It's a little bit more complicated logistic regression. Here, you're just using the standard next token prediction for this SFT. Yeah, it's also, I mean, also called rejection sampling, best of K. Yeah, here, I mean, it should be, I just say top one. Yeah, top one out of K. Best of K is top one out of K. Yeah, and there are some terminology I need to change. But basically, yeah, this is what it looks like. Okay, so once you have that, what is the algorithm? The algorithm is for each stage at any t or t plus one, you alternate among these steps, right? So first, your data collection. This is your prompt. Your prompt, getting a batch of prompts. For each of this prompt, generate k candidates with a certain temperature. This one should, yeah, I think I changed a little bit terminology because this one is using that paper. I copied a little bit from that paper. This slide, maybe I will redo this just so that we don't have a change of terminology. But essentially, this is in our terminology, it should be A1 up to AK. And this one is a little bit with is a generative model at stage T at a temperature tau. So for example, usually temperature you can be a little bit smaller than 1, which give you a little bit higher quality results. So that's when you do the generation, right? You can generate some temperature at 1, or generate be smaller than 1. So at least in this paper, it's talking about generating instead of with temperature 1, you can generate a temperature a little bit smaller than 1. So this is how it works, and keep 1 per prompt in ranking. So acceptance ratio is 1 out of K. So it's not top K, yeah. So that's why I need to modify the slides. 1 out of K. And then that's it. Yeah, that's I think that then data ranking is computed with this guy, right? Collect this. Yeah. So basically you have this. Yeah, I will change from Y to A. Y is in the paper. So when I copy that, I think I just forget about our terminology. So AI. And then you might find SFT. Once you have that, you already have a sequence. This is your SFT data, right? You just do, for example, 1 iteration. You really don't want to do many iterations because it's a small batch. And then you, if you do more than 1 iteration, overfit to that batch. But you just do one iteration, right? Then you are okay. So then you just keep repeating this. So then you are done. So yeah, so basically this is an idea about this algorithm. So I hope this is clear, although there's a change of notation, but hopefully this is still clear, and I will change it back. Hyperparameters, so quickly mention these hyperparameters. And then you see, this is I would say this is probably the simplest RL framework, right? So now then you can have better understanding when I give you the hyperparameters, batch size, right? This is generating a batch. This is not a training. This is not a SFT batch size. This batch size, SFT could be a smaller batch size usually, but this batch size is a generation batch size. K is acceptance ratio. Usually it's 1 over K and so on, right? So tau is this one say 0.8 instead of 1. Right, 1 is a typical generation temperature, 0 is a greedy temperature, and usually when you do the generation, you see something close to 1. Even when you do the applications, right? You many cases you do things close to 1 but not 1. Let's say 0.8, which makes it generating a little bit more higher quality data. But the larger tau will be more diverse. The quality may be sometimes be a lower quality, so there are trade-off. with this temperature. Beta is KL regularization, and so on. T is iteration, and so on. Yeah. So basically, this is what it is, and they just looking at some examples of these results. This one says the following. So basically, you have again, you know, PPO is it's very difficult to implement. So this may not necessarily be the best implementation of PPO, but the same as that, we don't have a very strong implementation of PPO because it's very tricky. Anyway, so this one is K is 32 over 1, and this is a K over 8, and so on. So basically, just try to look at this eval. So yeah, so evaluation. You use this guy, you generate. So basically, this is at least it is easier to tune. So that's why you are better than PPO, right? And everybody, I mean, when they compare PPO, they say it's better, but the PPO is not that easy to do. Yeah, and here is just say basically this is a hyperparameter tuning, right? So you say, oh, K32 is better than K8. Yeah. Just look at the win rate. Yeah. So that, yeah, that's about it. Right. So basically, yeah, this is that. So this is coming from this paper. Then I think that's about it. There are some more examples we can go through a bit. So how do you, yeah, this one is an example of this particular alignment data, which is released by Anthropic. Anthropic in early days, now of course they are best known for their agentic setting, right? Cloud code and so on. But at that time, they are more focused on the safety. So this harmfulness and helpfulness and so on. So this is something they care about. And basically these are typical examples, right? You have a human, or you have they ask you this thing, right? And yeah, and basically this is how it uses. And so basically this is one iteration, and the next iteration, so make it so there's something in it for them, and then ask then basically different response. This one is SFFT, this is a PPO, this it's just giving you. So yes, it's important, but you have to be careful. And SFT, this is a little bit more detailed. So right, so yeah, so PPO, yeah, this one is yeah. One thing I think probably, I mean, it's maybe for one example it's harder, but you give you a flavor of what it is. But one thing I mentioned probably earlier is this LAN, right? So when you do this RHF, usually you would, I mean, PPO because it's harder to tune, so we will ignore this, but just say this guy. SFT giving more details, right? RHF even here giving a little bit more details, but usually that's typical. So you have to normalize the lines. You say, okay, do not answer too many, but people generally prefer longer answers. So that's a fact. It just, even you are saying something not necessarily that informative, sometimes it gets preferred just by the preference. And the RHF will allow the language model to learn such preference, give a more detailed instruction, which actually in some sense is good. In some other sense, it's just generating some it's just generating the longer length rather than giving more information. But in some other sense, it's just giving you a better in terms of human preference. So yeah, and so on. Yeah, but basically, you know, this is just an example to say what the effect of this RHF will give you. So in this kind of example, reward and KL versus RHF. So this one is again just some experimental results. The algorithm is pretty simple. So the algorithm compared with the DPO, again, it's really in the policy update stage, you work with SFT data rather than preference data, right? DPO can work with preference data, and Raft works with SFD data. But otherwise, they also have a different ways of choosing. DPO, you give a pair, right? And you keep both pair. If you have Raft, it will say pair of size 2. You just pick the top one, right? So it's a k equals to top one. So compare with that. So basically, yeah, they both RL, but using a different ways of learning and a different ways to get your how the data should be prepared. Reward and KL. So this one is iterations. Test reward keeps going up, right? So and here is KL also keeps going up. Basically, it just says if you have a larger penalty, your KL will be going up smaller, which is understandable, right? Because you know. Because you have more constraints. So basically, just say you put control the KL and versus reward, but this one is a separate KL and the reward. This actually, another thing is for the Raft is it's a very generic algorithm. It's not even talk about a language model, right? So in the DPO, if you think about that, you need to have a probability model because they're using a relationship of a probability model and the reward, right? There needs to be a probability model. In this guy, it doesn't necessarily be a probability model. Diffusion, it's related to so-called energy model, which is a probability model, but it doesn't really, it's more implicit, not explicit. So therefore, you couldn't easily get a probability model out of a diffusion, which is image generation. But you know, as long as your reward model, you could use a Raft type of method. So this I could use quite a bit in the setting of this kind of image. So this one is an example. It's a text image alignment. And so the key is Raft does not require a probability model, only require generation plus filtering using a reward, right? But whether your generation is a probability model or not doesn't really matter. Here's one example about this. Also, there's more in the paper. One example of this one is a Monad style cat, which is a diffusion 1.5, which is in academic, people generally use this one, even nowadays using this to do experiments. So this is a reasonable image generator, and it's a smaller scale, so it's not too costly. Right, you can fine tune that and so on. But here, you know, either give you a cat or you give you a bridge, which is you do see it's like a Monad style, but you know it's kind of missing the cats or the strange position of a cat and so on. Right. So basically, you see something not as aligned. It have not always aligned. Here you see much more alignment. Of the cat versus style, the style of of that. So basically, you say you can Raft aligned using the so-called score clip. We will talk about in part 3, which is a part of score. You can treat that as reward model to match how the text and the image align. Is this text and image aligned or not? And once you increase this score, which means they are more aligned, right? They're both aligned, will be both monad and cat, right? So here, yeah. So this is one example about that. There are other examples again. You can use a quality score to do that as well. There are also image quality score, just what image looks nicer compared to other image, and you can use that as reward model to train. So there are a lot of reward model you can use to tune your generator. There are DPO variants which work with this image generation as well by using RL, but Raft is actually the simpler to use because it doesn't require anything, small model. And also I know that it's used quite a bit in practice, so in the industry. So DPO turns out to be more in academic. They also use in the institution, but I would say you use the more in academic than the industry. But like selection sampling, rejection sampling, raft type of idea used more, at least in the industry, because they are simple and effective, this kind of approach. So yeah, so I will just give a summary. Both, I think, for the raft versus iterative DPO, also you can think about the supervised learning versus reinforced learning, right? So these two algorithms basically essentially tells you what reinforced learning should be look like. And this one will also go next time. We'll talking again in this kind of a framework, reinforced learning framework, right? It fit general RL training. Policy generate the data. The prompt is not generated. It's just generating data in terms of response, right? Score ranking. Score is used in the, actually you can say both is ranking in the iterative DPO versus RL. It's just what you keep, right? In the iterative DPO here, what you keep is basically your top ranked data, both data, pairwise data. In the raft, you keep only the top ranked data. So raft is simpler. You update, one is SFT, one is preference learning. So, but both fits this framework. This is a typical reinforced learning framework. One thing I want to say a little bit about this reinforced learning is this kind of because it generates your own data, right? There are some desirable effects. Why this become very popular in the large language model, even for the reasoning, and later which we'll talk about next time, is when you generate your own data, somehow, as long as you have a good reward model, right? Somehow you can say the data generated is good in the sense because it's evaluated by whatever criterion you want to evaluate. You always try to optimize your own policy, right? So instead of a supervised learning like SFT, for example, which has a issue with once you optimize your policy, it may have a distribution shift. Reinforced learning has a less distribution shift because of this. The only thing could be reward hacking, but not for the policy generation, because policy you're starting to generate data is the same as what you train about. SFT, when you train the data, when you generate data, they can have a different distribution. So that's why it's a little bit tricky. And this is also one of the reasons why people use quite a bit of reinforced learning in the large language model, or nowadays in other settings as well, is to do with the way of this kind of framework allow you to use your own generated data. This kind of prevent distribution shift, or at least it's a part of the goal to make sure your distribution shift is better controlled. So this one is observed somehow in practice. Raft per stage, right? K candidate ranked and keep the selected response, just the top one. Then you have SFT. So this is a key difference about these two procedures. While the iterative DPO, your chosen versus rejected pairs using your reward model, right? Updated with preference optimization instead of SFT. So this is a key difference. Otherwise, they all fall into this RL framework. Trains on select single response, this pair preference data. So that's essentially the key difference. But otherwise, if you think about these two algorithms, once you look at it together, which is good to look at them together, then you understand that they are all formed with the same framework. So it's just two different. SFT, of course, is easier, so that's why this one a little bit more preferred in some industry. This one is still used, but used lesser than this one. So the references, this is important paper, direct preference optimization, especially very favored in academic. There are a lot of people using that because it's bypass reward model. This one just say you should make it RL rather than supervised learning. This one is just supervised learning. This one is RL. And this one is also RL. Just say this one I think is similar time. Actually earlier. yeah, but then you just say, yeah, basically, this one just says that you can use SFT. This one is, from novelty point of view, this one is probably a little more novel. This SFT people kind of know. This one just say, oh, instead of SFT, you can actually use preference optimization directly. So, but otherwise, both are the similar. So, yeah, I think that's all for this lecture. Next time we'll talk about continuation about this reinforced learning, but more focus on these training reasoning models rather than alignment. This is for alignments. Next time we'll talk about reasoning models. Okay, and then we will done with the LLMs. Okay, so okay, thanks. Any questions? If not, then that's all for today.